just want to give you intuition for conditional typical subset. We also saw it in the other course, but let's redo it. So it just basically retakes the fundamental concept of information theory. Imagine you have a communication channel that is noisy. For example, a telephonical line, you want to call your mom, but there is like some tomato on it. So let's create the channel. And so let's say you have all the possible channels at the beginning without all the entries at the beginning. So what you can say. And after the y to the power of n, like all the sequence imaginary at the end. So, because of tomato, it would be less bigger. And so conditional typical sets, because of the noise of the tomato, the 30 the exit y can vary. Like, for example, the noise have a noisy statistical law, and so it can create a conditional typical space regrouping the type of sequence you can have. So if there's maybe the tomato like block all the v, all the a words. So if you say now all the o words, so if you said hello, your mom will hear hell. Hello, I like tomato, and so she will hear the hell. I like hell. I like so yeah, that's an example. It blocks all. You have a less typical subspace. And so the formula about it is just like if you check your exit alphabet y and you count the number of symbols to it, we can say there is y different symbol. So for example, it's a binary, it's like 0 and 1. And we have y to the power of n sequences, so 0, 1, power of n. And so because you're in information theory, we count in bits in base 2. So we must use mathematical equality to represent all the sequence 2 to the power log of 2 of yn, which is like 2 to n log 2 of y. So that literally is a maximal space at the exits without taking into account the probability of events. So it means like you have the O that can pass through, for example. Or no, maybe we blocked all the O, like we block like all the A 10% of the time. And so if you have 10 words with A, for example, 100 words with A, not all of them should be blocked. And so the A, like you can like exclude this from Y, and it will be the typical subspace. So we have the conditional entropy that measure uncertainties that stay on Y, one we know X. So all typical sequence, conditional typical sequence are less or more equiprobable, each of them having a probability of less or more 2 to the power of minus n of h, y, 9x. And yeah, so all the conditional typic sequence like has this probability. And because the sum of the probabilities should be 1, the number of the sequence is like the inverse of them. So it's like 2 to the power of n of ha of y knowing x. So that's just a number of exits that is possible because like this is the probability of them that happen, and because you must sum them to 1, then that's the number of exits. And because entropy is always inferior to the total number, we can write this. Well, either way, like you have a big space and the little space, so the little space will be less bigger than big space. And so when n increase, the typical set like became really low in comparison to to the the size of the all the exit space, and that thanks to this concentration that we can find if useful correction code. It's directly linked to compression that we've seen, you know. The more the message, the longer, it's a lot of bits. The more like you can compress like all the information into little information, because like you know like it is a typical subset that can is like the more probable, and yeah.